Hey, I'm sorry to those of you looking on the video, I forgot to turn on the video. Or I should say, the whole class forgot to remind me to turn on the video. So all we have is the audio, but you can follow along to the audio by looking at the exam solutions and get most of the benefit. Okay, so these are the slides we were looking at. It's been a couple weeks now, about the setup for cryptography. So we've got Alice wants to communicate with Bob using some encryption algorithm. So Alice encrypts her message using the encryption algorithm. Bob decrypts it using the decryption algorithm. And we got Eve in the middle that we assume knows what algorithms are being used and intercepts. We assume that Eve can intercept the message in transit. So we've got to try to make it so that it's secure for Eve's attack. And we looked at one-time pad, and the idea behind a one-time pad was basically, was to take your message as a string of bits, take a key, which just generate a random string of bits the same length as the message, and then XOR the bits together. So basically, you are flipping a coin on how to encrypt each bit. And each bit is encrypted separately from the others. There's no relationship. The first bit is encrypted by a random choice, and the next bit is a completely different random choice. And I said that was a completely secure, unbreakable system. So let me ask you this. Suppose you take let's say a 1,000-bit message, and you generate a 1,000-bit key, and you encrypt it using a one-time pad. And someone intercepts the encrypted 1,000 bits. Okay? They know the key was 1,000 bits long. What's to stop them from just trying all 1,000-bit keys until they get a message they can read?
Because that's 2 to the 1,000.
Okay? So that's 2 to the 1,000th, which would take too long. But suppose they were really patient. Could they, in principle, decrypt it? They just keep using keys, just generate one key after another, 2 to the 1,000th of them. Would they eventually reveal the message?
Yes.
Yeah, but why is that not even a threat? Yeah.
They wouldn't know if that was actually the right message or not.
Right. They wouldn't know if that's the right message. They would reveal every possible 1,000-bit message. There'd be lots of perfectly fine English strings with 1,000 bits in them that would be revealed. And there would be a huge number of possible decryptions that make sense in English, if it is English. Which one was meant? All they know is what they knew going in. The answer is 1,000 bits long. So anyway, why don't one-time pads work so well in practice?
Getting the key to the other person is a little difficult.
What was that?
Getting the key to the second person.
Transmitting the key is the problem. The key can only be used once, and it has to somehow get to the other side, same as a message. So key transmission is a killer there. Okay. So the Advanced Encryption Standard was adopted in 2001, AES, and it was adopted because the old technique that was used for commonly used for encryption, DES, Digital Encryption Standard, had been adopted maybe in the 70s, and it had outlived its useful life. And so there was a competition for research groups to propose a new standard, and this one was adopted. And this is called a symmetric cipher, a symmetric block cipher, because the key K that's used is used on both sides. So Alice encrypts using an encryption algorithm, a message using a key K, and on the other side, Bob has to know K to decrypt X prime. So they got using a decryption algorithm. So they're using the same K, and so there's a key transmission problem there as well. But the key can be reused. It's not a one-time use like a one-time pad. So there's a deal. To send a message, Alice and Bob must agree on a random 256-bit string K. Then Alice breaks the message into 256-bit blocks, encrypts, and sends. Encrypt the next block, send. Encrypt the next block, send. And basically, you can think of the encryption algorithm as using K to map every 256-bit sequence to a different 256-bit sequence. It's just sort of scrambling up a gigantic alphabet. to the 256 letters in it. D just does the reverse mapping. The key can be reused. It's a symmetric block cipher. Symmetric because the same key on both sides. Block because we're breaking the message into blocks. One way to decrypt is the same way I suggested, trying every key. Now, with the same argument that I just made, I just argued that one-time pad, if you try to decrypt with every key, you wouldn't get any information out because you wouldn't know, you'd get lots of perfectly fine readable messages out, but you wouldn't know which one was the one that was encrypted in the first place. Could you make the same argument here? Yeah?
If you test all the keys and all the blocks, you can cross-reference them.
Okay. So the point is, besides the point that it would take a very long time. So AES is secure, among other reasons, we're believed to be secure, because it would take too long to try all the keys. But if you have a long message and it's been encrypted in 256-bit blocks, if you find a key that decrypts the first block into something sensible, and the second block into something sensible, and the third block, and the fourth block, and the 10th block, and the 100th block, that's probably the key. Okay? So the difference is we're encrypting by blocks instead of encrypting the whole message. Instead of encrypting every bit separately, we're encrypting every 256 bits separately. So the blocks aren't independent of each other. And if you find a key that works for every block, that's probably the key. Yeah?
You said we're transmitting the key as well, right?
Well, I didn't talk about how we're transmitting the key. That's the problem. Key transmission. Okay? If you can get the key to the other side, then it's great. Okay. RSA is named after its inventors, Rivest, Shamir, and Adelman, who were university researchers, professors, in 1977. And it created quite a stir in the government, the U.S. government. The U.S. government immediately tried to squash the research. They tried to prevent it from being published. And that didn't work. They tried to have a deal where you couldn't publish unless you ran it by them first. By them, I'm saying the National Security Agency. That's sort of the U.S. government's code-breaking agency. They didn't like the fact that there was a code they couldn't break. And finally, that didn't work either. The U.S. government classified RSA technology as a weapon and then prohibited its export under an act that prohibits the export of tanks and nuclear bombs until 2000. Bill Clinton, one of the last things he did in office was remove the export restrictions from RSA because, after all, other countries have programmers. And if you can't get you can't get RSA export in the U.S., you just build it in China, right? So they removed the restriction. But I can remember, like when the first browsers came out, and they had encryption built into them. There was a secure. There was they called it strong encryption. A strong encrypted version was available inside the U.S. and a weaker version for export. So I guess it wasn't RSA. I said RSA couldn't be exported. RSA using long key links could not be exported. There's a whole long political history of the government fighting against this, and the government finally either just gave up on it or broke it and didn't tell us and didn't care anymore. So people debate about that. And as we talked about last time, to receive a message, Bob has to have a public key and a private, has to have a pair of keys, a public key and a private key. And to send a message, Alice needs to know that public key, but does not need the secret key. So that solves the key transmission problem. Because what Bob does is just generate the key and then publish the public key. And the secret key never needs to leave Bob's possession. So as long as Alice has that key, the public key, she's in business. So here, it's also a block cipher, but the block links are a lot longer. So 10 years ago, 1024 bits was common. Nowadays, 2048 is the minimum. simply because computer speeds have gotten faster and certain brute force attacks became feasible. So just, it works the same idea as an AES, a completely different algorithm. But you break your message up into 2,048-bit blocks, and you encrypt them a block at a time. And each number in that range, from 0 to 2 to the 2,048 minus 1, maps to a different number in the same range. And then you send the bits over, and then Bob decrypts with his secret key. And it has this interesting property. If you take a message, a block, and encrypt it with the public key, and then decrypt it with the secret key, you get X back. But also, if you take X and encrypt with the secret key and decrypt with the public key, you get X back. This is called encryption. Encrypting with the public key is called encryption. Encrypting with the secret key is called signing. Now, why would that be called signing? In what sense? If who could encrypt a message with the with S sub B? Yeah. Well, could Alice increase the message encrypt the message with S sub B? No, Alice doesn't have S sub B. There's only one person that can encrypt with S sub B, and that's Bob. So suppose someone gives you, suppose Bob takes X and signs it with his secret key, and then publishes it and says, here is a document guaranteed to be from me because I encrypted it with my secret key. How could you test and see if he's telling the truth?
Decrypt it with the public.
Right. You get the public key, which is public, and decrypt it. And if you get a document back, then yeah, it was signed by Bob because only Bob could have signed it. And so we're going to end up using both of those properties. When we do e-commerce, we're going to use AES and we're going to use RSA. We're going to do e-commerce encryption. We're going to use both algorithms, AES and RSA. And we're also going to use both encryption and signing in RSA. So all these things fit together to make to add up to encryption in RSA in e-commerce. All right. So we assume that Eve can intercept the message and that Eve knows Bob's public key. And it is believed that this doesn't help her break the cipher. And the problem with RSA is it's inefficient. The computation that's required to encrypt, you have to do a modular exponentiation of a bunch of 2048-bit numbers. And modular exponentiation is n cubed, where n's the number of bits. So it's slow and getting slower as the bit length get longer. Okay, now we looked at the algorithm. I skipped ahead last time and showed you the algorithm. So let's just remember what it was. You take two distinct primes, P and Q, nowadays each at least 1024 bits. You multiply them, that's the modulus, n. You define a number phi, which is just P minus 1 times Q minus 1. You select a number E greater than 1, whose GCD which is relatively prime to phi. E is the public exponent. You choose D, so it's the modular multiplicative inverse of E, working mod phi. We call that the private exponent. And then the public key is E and N taken together. And the private key is D and N taken together. So really, all that's secret, all you have to keep a secret is D, because the N is in both places. So D is what the secret is. So we know that the eavesdropper has the public key. So what is the obvious attack to break RSA?
Try to factor in.
Factor in. If Eve can factor in, now she has P and Q. And that's all she needs to recompute everything. So if she can factor it, she can figure out D. If she knows D, she can decrypt anything. So RSA is secure, believed to be secure, because it's secure in practice because no one has found a fast way to factor large numbers. Is it secure in reality? No one really knows. No one has proven that it's difficult to factor large numbers. So it's kind of a bit scary.
Why do you find a fast way to factor
Why do you have to find a fast way to factor in?
Uh-huh.
Well, it doesn't do, if it takes you 100 years to break, to steal someone's credit card number, it's not going to pay off. Yeah, typically you need, well, I'll show you, I'll have something to say about that a little bit later. All right, and the encryption algorithm is just simple. You take the block, you raise it to the power E, mod it. Single modular exponentiation encrypts the block, and a single modular exponentiation decrypts the block. Just use a different exponent. And here's the example I showed you last time. You take P and Q, which is 3 and 11, multiply them to get N, that's 33. Phi is just P minus 1 times Q minus 1, that's 20. The smallest E we can use is 3, because 2 doesn't work, because it's not relatively prime to 20, but 3 is. D is 7. 3 times 7 is 21. 21 mod 20 is 1. That's good. And so our public key consists of the 3, which is E, and the 33, which is N. And S consists of 7 and 33. And you got a problem like that on Caddis, and I think a different problem actually in the assignment where you compute these things. It's not hard to do, if the numbers are small. And clearly, you wouldn't want to use RSA using such small keys because 33 is easy to factor, right? That's why you have to use long ones. All right, and this just shows you some of the result of encrypting. So using these small keys, if you want to encrypt 4, it turns out it goes to 31. If we decrypt it, it goes back to 4. So nothing groundbreaking in these tables. It just shows you that it just sort of scrambles the numbers up. Every number in the range up to N minus 1 is mapped to a different number up to N minus 1. And this table, if you wrote out the table here, it'd be pretty big. If you wrote out the table for a 2048 bit N, it would be 2 to the 2048 lines in it. So you couldn't possibly store the table, but you can compute any line, any row in the table easily. Yeah.
Let's say you're the one that wants to send an encrypted message.
Mm-hmm.
The other person is gonna have to know the secret key for only you.
Nope.
No?
If I'm trying to send one to you,
Yeah.
yeah,
Let's say
yeah,
trying to
you're
send
going to have to know your secret key.
But wouldn't you only know the secret key?
I don't need to know the secret key. I need to know your public key. Because remember, to encrypt, I raise x to the E mod n. E and n are the public key. And then once you receive it, you can decrypt it with your private key, D and N. So that's the beauty of the algorithm, is I can send you a message that I don't know how to decrypt. Everyone in the room could do that. But since you're the only one that holds the secret key, only you're going to be able to decrypt it.
So what RSA basically means is anyone can receive a message, but only the person receiving that message can decrypt that message.
Right, RSA, public key encryption, anyone, the assumption is you publish your public key in the phone book or whatever. Stick it as an attachment to your email. Anyone that has that public key can send you an encrypted message, but only you can decrypt it. Because the public key doesn't help you decrypt messages. Only the secret key can do that. Yeah?
You were saying that the public key includes one prime number and
No.
the product of the two prime numbers?
No, it consists of n, which is the product of two primes, and this number e, which we computed. E is 3 by coincidence here.
Oh.
E is just a small number relatively prime to phi, which is based on P and Q. Yeah, but don't read anything that E and P are the same there. But it's just a coincidence. Yeah.
You also mentioned that having the private and the public key take a long time to configure, but in theory, does that mean that once you've made your public and your private key, you can use them as long as you want?
Yeah, yeah. So typically, you create a private key, you might use it for use. You put an expiration date on a key pair, just so you're forced to replace it before technology catches up. because as computers get faster and better factor algorithms are discovered, they have to make the key length longer. And so keys that were used in the old days wouldn't be secure today. Yeah?
Going back a little bit, what would be the point of signing? Like, why would somebody ever do that?
Okay. Utah was the first government in the world to allow digitally signed documents. So they gave, using, and the signing technology was this RSA-based thing. And it had the same force in law as a physically signed document. It was also one of the first to repeal their law because no one made use of it. But it's I don't want to get ahead of myself. Signing is a absolutely key part of e-commerce. So we'll get to that. Maybe not today, but next time, early next time. You'll see what I'm talking about. Okay. So I mentioned that encrypting with the public key and decrypting with the private key is encryption decryption. And that's used for security. Encrypting with the private key and decrypting with the public key is signing and verification when you decrypt it. That's used for authentication. So the idea is if something was signed with a private key, you can verify it by decrypting it with the public key. And but only the private key holder can sign because they're the only ones that hold the secret key. Yeah?
So would that technically mean that any messages sent through with the private key are not technically secure since the public keys are public?
Oh yeah. Yeah. If you encrypt with if you encrypt with the private key and transmit it, anyone can read it. And the fact that they can read it by decrypting it with the sender's public key proves it came from the sender.
Mm.
Yeah.
How is it then that you can, like, if you're sending an email, you can sign and encrypt it?
Well, I could, first of all, signing and encrypting in that context don't necessarily refer to RSA. But suppose it did. Suppose we're talking about RSA technology. How would I sign an encrypted email? What would that mean? Yeah.
You could first start by encrypting the email itself.
Okay, I would encrypt it with,
Your private key.
well, encrypted means, let's say I'm sending to you. I would encrypt it with your public key so that no one can read it except you. And then encrypt it with my private key to sign it so that when you receive it, you know it came from me. So when he receives it, the fact that he can decrypt, he can verify the signature by decrypting with my public key, so he knows it came from me, and then he can read it by decrypting it with his private key. Everyone else can verify it came from me, but they can't read it because it's encrypted. Yeah.
You mentioned that you can make RSA more secure by making the keys longer.
Mm-hmm.
Couldn't you recursively do it, like having a bunch of keys and encrypting it or encrypting it and encrypting it instead of doing one key sending 5?
Well, if a certain key length is vulnerable, if you're using a key length that's not long enough, and you encrypt it with 10 keys, you encrypt it 10 times with different keys, yeah, you've got more work to do to break it, but it's just 10 times as much work. Whereas if you add a bit to the length of an RSA key, you have doubled the number of possible numbers. And doubling the length really adds up. Yeah?
What's the advantage of encrypting and then, encrypting and then signing over signing and then encrypting?
There isn't a difference.
To the end, to the person I'm sending it to, there's really no difference. I guess one thing, if I signed it first and then encrypted it, and then sent it out, anyone that intercepted it wouldn't be even able to trace it back to me because they couldn't verify it. So that might be a better way to do it. Depends how much I care about my anonymity when I send it. Yeah.
A question about the history of RSA. Is it true that the inventors picked two large prime numbers and then just basically kept the secret to themselves? And then as time goes on, they increased the size?
The inventors of RSA pick two prime numbers. Basically, any user of RSA picks two prime numbers and computes a key.
I see.
So if you wanted to use RSA, you know, like there's PGP, pretty good privacy, which is a publicly available public key encryption system that got its inventor in trouble with the government. They tried to try him for violating that Arms Export Act. What you would do is you would install the software and then direct it to create a key for you, a key pair for you, and at that time it would generate the 2 prime numbers at random, and then generate the key, and then you would hold the secret key on your computer and not share it, and it would and then you would export the public key. Okay, now, sort of 2 things I want to do. The first thing I'll do today, the second thing I'll do next time. One is, what I'll do next time is show you how AES and RSA are used together in e-commerce to make it all work, and how verification comes in. The other thing is, I want to show you the proof that RSA works. And it's easy to sort of shut your mind off and say, oh, this is a proof, I'm not going to pay attention. But I think the cool thing about this proof is you can understand it. It's not complicated. It just makes use of these, it makes use of the algorithm up there, and it makes use of Fermat's little theorem to prove that RSA is correct. So I think, I've skipped over a lot of proofs this semester, but I think this one is worth looking at because it is, it's cool that such a groundbreaking thing has such a simple proof. One thing I should mention is when RSA was invented in the 70s, it really didn't have a use. The big use case came when there were web browsers and e-commerce started. So it was sort of a solution looking for a problem for a while. So we want to prove that if you take x and raise it, and x is a number that's got to be smaller than n, x to the e power to the d power is the same as x to the d power to the e power, and that's the same as x. So you encrypt and decrypt, or you decrypt and encrypt, you get x back. Mod in. Okay? That's just the definition of what it means to be correct. All right, first thing I'm going to assert is, let's take ED, and I claim we can write that as 1 plus k times phi, where k is some integer. Okay. Where does that coming from? How do we know that ED is 1 more than some multiple of phi? From 5. Right? 5 says that ED is the same as 1 mod phi. So maybe ED is 1 plus phi, or maybe it's 1 plus 2 phi, or 1 plus 10 phi, or 1 plus a million phi. But one of those k's will work out. So that comes from number 5. Okay, so now we can write, anywhere we see ED, we can write 1 plus k phi. All right, that's what I'm doing there. X to the ED minus x is the same thing as x to the 1 plus k phi minus x. Now, what would I expect? If RSA works as advertised, what should be the value of x to the ED minus x? If we're working mod in. 0. Because we're trying to prove that x to the ED is equal to x mod in. So we expect that difference to be 0 if you're working mod in. Then I'm going to factor in x out, so I get x times x to the k phi minus 1. And then I'm going to write x to the k phi as x to the k times the p minus 1 times the q minus 1. Now, why do you believe that? Because of 3. That's just the definition of phi. So I'm substituting, expression involving p and q for phi. So as you're looking at this proof, I'm not expecting you to figure out how they came up with the proof in the first place. The idea is just to try to convince you that each step makes sense. So that's number 3 there. And there I'm just rearranging things. So I had x to the k, p minus 1, q minus 1. I turned it into x to the k times p minus 1, all raised to the q minus 1 power. So that's just a rearranging exponents deal. And then comes the surprising thing, maybe. If we work mod q, that massive expression up there is 1. So how are we able to say that x to this exponent raised to the q minus 1 power is 1 working mod q? What justifies that completely? Yeah, that's just from Oscillator theorem. Q is a prime. Q minus 1 is less than q. So we get 1. That's from Oscillator theorem. So what we're saying here is that means that x to the k phi minus 1 is divisible by q. Now where did that come from? I mean, what we showed was that x to the k phi was 1 mod q. So x to the k phi minus 1 must be 0 mod q, which means it's divisible by q. So we got that right there as divisible by q. Now, I'm also claiming it's divisible by p.
Same reasoning.
Same reason. Up here, I rearranged, when I went from this x times k to the p minus 1, x to the power k, p minus 1, q minus 1, I factored out the q minus 1. I could have done the same thing and factored out the p minus 1. And gotten the same result here for p. So we've got this number here that's divisible by q and by p. And q and p are different. So what else is this number going to be divisible by? It's divisible by one prime number and a different prime number.
Divisible by n.
It'll be divisible by their product. If something is divisible by 3 and by 5, it's divisible by 15. So we've got something that's divisible by q and by p, so it must be divisible by p times q, which is n. Okay, that's just from number 1 and number 2. So we're left with, we got x e to the d minus x, which is equal to x times x to the k phi minus 1. How can I say that this is 0 mod n? In other words, I'm saying that this number here, x times x to the k phi minus 1, is divisible by n. That's what would make it be 0. Yeah?
Since x to the k phi minus 1 is
Right.
divisible by n.
Since x to the k phi minus 1 is divisible by n, x times that thing is also divisible by n. But that's what we're trying to prove. We just proved that x to the ed minus x is 0 mod n, which means x to the ed is the same as x mod n, which is what we're trying to show in the first place. So, yeah, I mean, there are a lot of steps, and you may get to the end and not remember how you got there, but it is well within your power to understand how each step works. And, the only theorem we applied was from Oscillator theorem, from 1640. So, I doubt he knew this how it would be used, but that's how it's used. All right, so next time we'll go from the theory to see how it's used in practice.